Hi, I'm Pyungsoo Park and a fourth year PhD student at Seoul National University. My research interests are in system architecture design and implementation, including systems for machine learning, artificial intelligence, memory, and storage. In this video, I would present our work, TrainBox, on extreme scale neural network training server architecture by systematically balancing operations. This work is done with my fellow student, Hee-Taek Jung, and my advisor, Professor Jang Kim. Nowadays, neural network becomes one of the most important workflows for system designers. Neural network shows high potential for many labor-intensive tasks, from classifications to autonomous driving. Before we use a neural network model for a task, we need to train it using a large dataset in many iterations. Therefore, its computation demands are very high, and the system designers start to focus on building high-performance training servers. As larger dataset and more iterations provide higher accuracy, we can easily expect that the scale of neural network servers continues to grow. Such large-scale systems rely on recent innovations in three aspects. The first is high-performance neural network accelerators, which reduce the computation overhead. For example, Google's TPU shows several orders of magnitude higher throughput than traditional CPU-based platforms. Second, the systems are now having multiple accelerators in a node and connect them using specialized interconnects. In this regard, NVIDIA DGX2 connects 16 GPUs using a high-speed NVLink, which provides more than 10 times higher bandwidth than PCIe interconnects. Third, ring-based oligos such as NICO provide scalable synchronization throughput so we can easily scale the number of devices. As a result, the systems are now ready to support extreme scale throughput for neural network training. Our paper is about the following question. What will be the performance bottleneck of the neural network training with these innovations? Now, I am going to introduce the performance bottleneck identified from our profiling at scale. Before we start, let me introduce the basics of neural network training. To use neural network, we need to have an optimized model for the task. The process to find such a model is called training and consists of three steps. The first step is data preparation. The CPU loads and pre-processes the data in the storage devices so that the data format is matches the model's format. Then, we give the processed data into the neural network model on accelerator, which compute parameter adjustment factors to tune the model. Lastly, the parameter adjustment factors from the accelerators are synchronized through interconnect so that we can get a globally synced view of the model. Neural network training repeats these three steps for a large amount of data and iterations to get reasonably high accuracy. To hide data preparation overhead, we typically overlap the data preparation with model computation and synchronization. This is easily achievable since the data preparation of the next batch is independent to the result of the previous batch's computation. Now, let's move on to our main topic of scalable neural network server architecture. The left figure shows the current server architecture similar to DGX2. From DGX2, we replace GPUs into neural network accelerators, assuming TPU-like performance. It uses SSDs to store the input data and accelerators to compute the parameter adjustment factors. In addition, it has two separate interconnects. The first interconnect is general purpose PCIe, which connects all devices in a system. The second one is the high-speed accelerator dedicated network, which only connects the accelerators. From the left architecture, we extend the number of devices in a server by exploiting the scalability of the two interconnects. To build such a system, we can use external boxes that have its own interconnect switches and down and uplink. By chaining the uplink and downlink of each box, we can easily scale the number of devices in a system. In this way, we can achieve scalability in terms of number of accelerators. But can you achieve throughput scalability? Unfortunately, our profiling results show that the answer is no, and we require a new server architecture. This figure shows the baselines for throughput scalability for 7 popular neural network models. To check the throughput scalability of the extended system, we virtually scale the number of accelerators and measure the system throughput. On a 2-socket Xeon platform, the throughput of the current server architecture saturated around the throughput of just 16 accelerators. That is, there is no practical gains after adding more accelerators after 16. To identify the reason for the limited scalability, we decompose the latency of the training. In this figure, we apply aforementioned innovations from left to right to see the bottleneck changes. Unlike common belief that model computation and synchronization take most of the time, at scale, the operations of data preparations, such as data formatting and transfer, account most of the time. So we conclude that many fast accelerators and high-speed interconnect have shifted the bottleneck to the data-related operations. Then, we check the resource requirement of the system not to make the data preparation bottleneck. From the resource requirement, we see that the requirements are tremendous for CPU, memory bandwidth, and PCI bandwidth, and a single system cannot provide this requirement. Also, we see that the requirements are different for each neural network model, so the system should consider this inter-workload difference. Now, let's dip into TrainBox. This is the overview of the TrainBox architecture. Like the current server architecture, we use multiple boxes to extend the number of accelerators in a server. On top of that, we design TrainBox with 4 key ideas. First, we deploy multiple FPGA-based data preparation accelerators to lower the CPU overhead. We offload data preparation functions into the off-the-shelf FPGAs so we can scale the data preparation throughput regardless of the CPU performance. Second, we adopt device-to-device communication to reduce memory bandwidth. We identify that the heavy DRAM bandwidth requirement stems from host-side buffering, which can be removed using D2D communication. Third, we exploit aggregate bandwidth of PCI switches rather than the bandwidth at the root complex by smartly clustering the devices. Because the device communication patterns in training is static and simple, we can exploit the aggregate switch bandwidth by making communication happen only within the box. Fourth, we use data preparation pool connected through Ethernet of FPGAs to provide workload adaptability. As each workload requires different amount of resources, finding an optimal amount of resources is impractical. Rather than placing many FPGAs in a TrainBox, we use a pool of FPGAs that can be used as a backup accelerators. In the following slide, I will explain the first 3 items in detail. Please refer to the paper for the data preparation pool. As the first key idea, TrainBox offloads computations of data preparation to an array of PCI-attached FPGAs for better throughput scalability. Compared to the CPU-based approach, which requires a tremendous number of CPU cores, this computation offloading frees most of the CPU resources. In addition, the scalability of the CPU-based approach is highly limited to the number of sockets on the motherboard, which is typically 2. Instead, our FPGA array relies on a scalable PCI fabric to scale the system throughput in a host-independent manner. As a result, we can scale the data preparation throughput without suffering from the CPU bottleneck. The second key idea of the TrainBox is to exploit device-to-device communication to reduce the pressure on the host DRAM. We noticed that the heavy pressure on the host DRAM mainly comes from buffer management. As we scale the number of devices in a server, the pressure of the buffer increases and limits the scalability. When we do CPU-based data preparation, these buffers are required for computation. However, the role of the buffer is now just data transfer because we offload the computations of the data preparation. In other words, the data preparation accelerator makes the host side buffer redundant. So, we decided to remove the host side buffers by applying direct D2D communication. We placed the D2D handler in the FPGAs to control the data communication without the host involvement. In this way, we can scale the overall throughput regardless of the host memory bandwidth. The third key idea is to cluster the devices to reduce the traffic at the root complex. As the PCIe is a tree structure, naive device placement makes the root of the tree a single point hotspot, which limits the scalability. Similar to the previous example, as we increase the number of devices, the traffic at the root complex also increases. From the analysis on the data communication patterns, we noticed that we can localize the data communication by placing relevant devices under the same PCI switch. Specifically, an input read from the SSD is consumed by only one FPGA and one accelerator. Therefore, if we place those three devices under the same PCI switch, we don't need to traverse the PCI tree all the way up. To enable this, we exploit the PCIe's packet forwarding mechanism that forwards the packets only to the destination. By deploying a separate box when scaling, we can achieve scalable performance by localizing the communication within a box. These figures show our TrainBox prototype on a real machine. We used the three FPGAs, one for TPU emulation, the other for data preparation accelerator, and another for data preparation pool. The left top figure shows the microarchitecture of the TrainBox's data preparation engine on the FPGA. And the right top figure shows TrainBox's system architecture. Finally, let's see the performance improvement of TrainBox. For the evaluation, we implemented a highly optimized software baseline on top of Caffe using the state-of-the-art data preparation library from NVIDIA. For TrainBox, we first prototyped small-scale TrainBox. Then, we made a performance simulator using the numbers from the prototype for large-scale TrainBox. For workloads, we used 7 popular neural network models for audio and image datasets. In this video, we mainly show the result of images, so please refer to the paper for audio results. First, TrainBox achieves higher throughput for all workloads over the baseline. We use 256 TPU-like neural network accelerators for these results. When we deploy a host-independent FPGA array, we get 3.3 times higher throughput. Still, there are much room to improvement due to memory and PCI bandwidth bottlenecks. Although we can apply D2D communication, the performance remains same because the pressure of the PCI bandwidth. Finally, when we apply both D2D and device clustering, we achieve another 13.4 times higher throughput. This proves that all optimizations of TrainBox are essential to achieve high throughput. Next, let's see the TrainBox's extreme scalability using Inception V4 as a reference. After applying only data preparation acceleration, the performance saturates around 32 accelerators due to memory and PCI bottleneck. In contrast, TrainBox achieves scalability for 256 neural network accelerators by applying device-centric data management. In conclusion, we identified a new performance bottleneck of the neural network training at scale induced by a recent innovation. Therefore, we proposed the TrainBox, a highly scalable neural network training server architecture, by reducing the pressure on the host side resources. Our evaluation shows that TrainBox is a very promising solution which overcomes the scalability limitations of the software-based approaches. Thank you for your watching.